Stop projecting first then stop projecting. Sir, can you stop sharing so that
Okay.
I can give the introduction?
Yeah.
Yes, sir. Yeah. So yeah, now we'll be having the session 13, that is day 6 by Dr. B.K. Chandrasekhar, sir, who is the
Advisor.
Advisor, technical advisor for Enerzi group of companies, and also he was the ex-director for Laird Technologies India Private Limited. And again, just to introduce once again, as sir had given already session number 1 and 2 on day 1. So I'll reintroduce him once again because most of them might have joined day before yesterday or today for that reason. So sir was also acted as a technical director for John F. Welch Technology Center, Bangalore. And also from 1984 to 2000, he was a deputy general manager at Ceramic Technologies Institute, BHEL, Bangalore. And 1982 to 1984, research associate R&D center at Grandwell Norton Limited, Bangalore. He was a postdoctoral fellow at IISc Bangalore. He has done his PhD from Pennsylvania State University and MTech from IIT Kanpur. He has done his MSc and BSc. Some accomplishments of Chandrasekhar sir is a expert member for Indo-Norwegian program on environment, ex-secretary Indian Ceramic Society Bangalore, ex-secretary Materials Research Society of India Bangalore chapter, ex-member Divisional Scientific Committee National Aerospace Limited Lab Bangalore, member Indian Society of Lighting Engineers, honorary invited faculty that is in manufacturing technology at IISc Bangalore, adjunct faculty at Manipal Institute of Technology Manipal, adjudged as best faculty for Edison engineers during 2004-2005 at JFWTC, invited lectures at Confederation of Indian Industries CII New Delhi, ITC Kolkata, Global Investors Meets Bangalore, and NTPC New Delhi. He has published papers in the reputed international journals. He holds several international patents. He has also delivered guest lectures on varied topics in national and international meetings. And one more important point is he is master in black belt in Six Sigma. Thank you, sir. Now the diet will give us.
Okay. Thank you very much, Dr. Ganesh. Are you able to see my slides now?
No, sir. You need to start sharing once again.
Okay, some problem. Just hold on.
Yes.
Okay.
Yeah, now we can see.
Went away? Came?
It went away.
Can you see now?
No, sir, not yet. Now we can see. Yeah, it's coming.
Okay.
Yes.
Let me expand it. Okay. Okay. Good afternoon to everyone. Namaste and namaskara to everyone. Again, I am substituting for Mr. Prakash Mughali, who could not be present today. I've been told that I should be talking for about 25 to 30 minutes at maximum. And so my talk today will be very brief. The topic today is basically what exactly are the emerging trends in the field of microwave processing of materials and their commercialization. This is kind of a very difficult to talk about because there are two ways of looking at it. One is what exactly is the trend globally around the world, including in advanced countries. And the other one is to look at it purely from the point of India and see where exactly we stand. As you all know that microwave processing of materials is an interdisciplinary subject. It involves knowledge of specific material fields like metallurgy or ceramics or polymers, and also knowledge of some kind of electromagnetic properties of microwaves, systems, processing of materials, so on and so forth. So it requires basically some kind of a team effort to make progress in this particular field, and any initiative that one takes is always a welcome step. We are all aware that in order to be competitive in any particular field today, we have to reduce our cost, including the energy cost, processing cost, and at the same time, we also have to be environmentally be sustainable so that our products are accepted throughout the world. And this is a challenge for most of the industries because especially with metals and ceramics, where high temperatures are involved, the consumption of energy is very high, and any even 5%, 10% improvement that we do to increase the efficiency is always a welcome. But fortunately for us, microwave processing of materials gives phenomenal advantages in this particular area because it reduces the consumption anywhere from 50% to 80%, which is very, very significant, without compromising on the quality of the product. Okay. In fact, in many of the microwave processed materials, the quality of the product is much better than that of the conventional method. Some of these things I have already talked about it in my previous talk, but in case you are new to this particular field, this may be an additional information to you. So let us understand in this brief talk where all we can use microwave material processing of materials using microwaves today. Okay, and also look at what exactly are the typical trends that we are seeing in microwave based manufacturing techniques. And we also look at some case studies, specific case studies, where the microwave processing has been commercialized and it has given specific advantages. Very briefly, it is almost a fairly mature technology in the advanced countries, and I cannot say the same thing about in the Indian context. This is relatively a new subject, a new field for most of the Indian manufacturing industries. We do see pockets of applications in different parts of India using microwave. A large number of laboratories do work on research and development on using microwave technology. But when it comes to industries, I must say that the usage is minimal, and it is for various reasons, and we'll talk about a couple of them at a later stage. As you know that AI and IoT are making huge impact in smart manufacturing technologies, and I am sure in the not too distant future, these things also will be used in microwave processing of materials. But let me talk about few applications. Some of them may be very interesting to you. We have already talked about the advantages of using microwave processing of ceramic materials in my previous talk, where we saw that cutting tools like tungsten carbide based cutting tools, we can reduce the temperature significantly and at the same time get a much better, harder and stronger material compared to conventional heating. Similarly, there are a class of material called titanates, basically barium titanate based perovskite structures, where the conventional processing techniques of 1300 degrees centigrade can be reduced to even 700 degrees centigrade, so that you get a superior product at much lower cost. Apart from this, it is very widely used in catalysts and increasing the rate of reaction in chemical systems, and this is being pursued by chemistry-oriented people in a very big way. Now, let me talk about, out of some interest, two specific industries a little bit in detail. One is on the food industry, and the other one is on metal processing. Okay, we touched upon metal processing also in the previous talk, and there were some few questions, and probably this talk I will make use of it to elaborate it further. The food industry, when we say, we all know that it is very widely used for cooking, but then there is a separate other discipline involving food industry, which involves sterilization of food grains. When you store food grains for a long period of time, there is always infestation of insects, worms, microorganisms, bacteria, viruses, so on and so forth, mainly because of humidity and temperature. This becomes a challenge, especially for people who export the products. Let us say that you are exporting basmati rice from India to a foreign country, and let us assume that the material is going by ship. When you load these materials in India, you do inspect the material and you found the material to be very good. And by the time it reaches the destination after a month or two sometimes, then you will find that the material has deteriorated because of infestation. And this is a very serious problem. And in the past, a lot of wastage was involved in such methods. Now, one of the ways to overcome this problem is to use some kind of a pesticide called as malathion. It's some type of a chemical, and when added into the stored grains in limited quantities, it is supposed to prevent the infestation of insects, and therefore this is a very widely used. But more and more countries object to the use of this chemical because they want a chemical-free product to be delivered to them. And the alternatives are that you use a gamma radiation or something like that before the food grains are sent abroad, not only for abroad, but even for consumption within the country also. But then this is a very costly method. So one of the alternative is to treat the food grains with microwave. Okay. So what happens is that when you treat the food grains with microwave, it destroys all the microorganisms that are present in the food grains, so that the reproduction of them is completely halted. And this practice is very, very widely used in advanced countries. I must tell you one thing very interesting, that India is an agricultural country, and we do export huge quantities of food grains to outside India. What normally happens is that the Indian companies export the material in whatever form that we send, and once it is received in the destination, those people give the microwave treatment, pack it again properly, and then sell it at a much higher price. This is known to Indian suppliers, but they don't do any action on that, in the sense that the same thing can be done within India itself at a much lower cost, and then exporting. Then by that time, the cost for the consumer also will be very less. but we will also make more value-added products. The second thing but unfortunately, this process is not very used in the country. We have brought this to the notice of the appropriate authorities in Government of India, but somehow it has not met the desired result to us. The other application of food is, that the drying of certain spices and herbs and so on. A simple example would be a red chili. If you go to northern part of Karnataka, where you are located, like Guntur, what is it called? A very famous place for chilies, Bellary in that area. In the seasons, they dry the chilies in the open air under hot sun for several days. The same thing can be done using a microwave within a single day, so that in case there is any cloudy day or a rain or something like that, the drying is not affected. And at the same time, the amount of dust that can accumulate because of exposure to outside and other things can be minimized. So apart from cooking, you can also say that sterilization can be one of the advantages of treating grains, so that the life or the of the product or the material or the food grains is increased significantly. I pause for a couple of minutes for any questions before I proceed next. Any question on this?
I think, sir.
Okay, let me proceed. Okay, I know this is a kind of off the field for most of you, because none of you probably are involved in any food industry. Let me come to the metal processing. Okay, we have already talked about this, and now let me talk about the sintering of metals and alloys. Okay, I'm sure this will be of some interest to many of you. The conventional methods of processing metals are all well known. For things like steel and other things, we have blast furnaces, induction furnaces, arc furnaces, cupola furnaces, and so on and so forth. And all these conventional processing results in very slow heating, long processing times, and many a times it leads to non-uniform heating with very high energy consumption as well as very high carbon footprint. So people are looking at alternatives so that some of the limitations of these methods can be minimized or reduced. And definitely microwave comes into the picture. Before I proceed further, in my previous talk, I had mentioned that one should not keep a metallic materials inside a microwave oven, because it leads to arcing and it can damage the magnetron, which is the source of the microwave ovens. But in the last 20 years or so, I would say about 26, 27 years, people have found that there are methods by which metals can also be processed just like ceramic materials or refractory materials, using microwaves by making use of certain interesting modifications to the process. And normally the microwaves have a tendency to get reflected from a metallic surface. However, when we make a porous metallic material, like for example powder metallurgy type of situation, it has been found that one can sinter metals using a powder metallurgy type of techniques using microwave, and the properties of such materials are found to be much better than that of the conventionally sintered metallic components. Now the question is that how is this possible? About 27 years ago, when this was discovered, at that time the understanding of the mechanism was not very well known, and people felt that somehow porous metals will absorb microwave energy and can, using that principle, one can sinter it. But in the last several years, a lot of theoretical work as well as experimental work has taken place. And now we have a better understanding of how to go about processing metals and alloys. And let me talk a few minutes on this particular aspect. Now, normally metals, let us assume a simple metal like aluminum, it will always have a thin layer of aluminum oxide, which is shown in brown color inside, outside, right? Can you see that? There are two circles. The outer portion is kind of oxidized layer, which has got a totally different dielectric properties compared to that of the inside actual metallic core. And this type of situation exists in many metals, including copper. Copper will have a copper oxide, iron will have an iron oxide, aluminum will have an aluminum oxide, so on and so forth. Okay. So when the microwave material interacts with such particles, it behaves differently with the outer oxide layer and behaves differently with the inner metallic core, which these two sections will have totally different dielectric properties. In the previous talk, we did mention that the heat generated depends upon the frequency of the microwave, which is typically 2.45 gigahertz, the square of the intensity of the electric field, which is E square, and also the frequency or the dielectric loss, which is called as the epsilon double prime. Okay. So what people have found out is that when you have a layer like this, then it is possible to heat a metal and sinter it to a fairly good density. And the additional work over a period of time has indicated the following. Now, when microwave penetrates a material, it gets absorbed many a times because of the dielectric loss, and the depth to which it penetrates is given by something called the skin depth. Basically, skin depth is nothing but the distance to which it travels inside a material, and it is reduced to about 1/3 of its original value. If the intensity at the surface is about 100, when it becomes about 33 or something like that, then that distance through which it penetrates is called as the skin depth. Now here I have mentioned the skin depth of typical conventional metallic materials, and most of them are in the order of 1 to 2 microns. Okay, and some of them are much lower, like stainless steel last row, stainless steel 410L, which is only 0.2 to 0.3. That means the microwave is fully absorbed at a very thin layer within that particular material. Now, in the previous talks, I always talked about the electric component of the electromagnetic field. But one should be aware that by nature, magnetic field also can take part in the heating of the material if the material is magnetic in nature. That means if the magnetic permeability is more than 1, then the magnetic component in the material will interact with the magnetic field of the electromagnetic radiation, that is a microwave, and can generate heat. Now, many of you may be aware of the difference between stainless steel and 316 and 410. I have some details of the composition. The 316 typically will have 16 to 18% of chromium and 10 to 14% of nickel, and 2 to 3% of molybdenum, whereas 410 has got 11 to 13% of chromium and very less amount of nickel. But the stainless steel 410 is highly magnetic because it has got what is called the martensitic structure, and therefore when microwave radiation is incident on that, because of the interaction of the magnetic field of the microwave interacts with the magnetic field of the stainless material, it absorbs very quickly and gets generated to heat, and therefore the penetration depth is less than a fraction of a micron. Okay, it's only 0.2 to 0.3. Whereas stainless steel 316, which is not magnetic, has got a skin depth of 7.57, which is a very fairly thick layer where the microwave can penetrate inside that particular type of stainless steel. Okay, and people have studied the behavior of these type of materials, and they have come to certain conclusions as follows. Normally, it was felt that finer the metallic properties, they absorb microwave more efficiently than coarser particles. But this was the original thought earlier, but that is not the case anymore. What they have found out is the ratio of the particle size to skin depth is the one that controls whether a metallic powder can be heated or not. Okay. These developments of theoretical calculations and modeling has helped us in understanding how the microwave interacts with materials. For example, if you are having a highly conducting materials like gold or copper and things like that, it is not the electric component that dominates the heating, it is the magnetic absorption that dominates the absorption. Therefore, the skin depth, if I call that as delta, actually there is a symbol for the skin depth which is a delta, but I could not download the symbol, so I just written as delta in quoted words. So if the particle radius is A, then if you can approximately make the starting particle radius to about 2.41 times the delta, that is the skin depth, then you are able to heat the material very efficiently. Whereas for weakly conducting samples, that means when I say weakly conducting, I am talking about weakly conducting, electrically conducting samples. The electric dipole absorption dominates when the conductivity is approximately about 0.45 Siemens per meter, independent of the particle size. That means you don't have to be bothered about the particle size when you are dealing with weakly conducting, electrically conducting samples, whereas for conducting particles, you have to be worried about the particle size. And people have found that, for example, for aluminum alloys, even a coarser grain of aluminum, one can sinter using microwave very easily and very efficiently with a very short duration time of less than 100 minutes, okay, or 50 to 61 hours, okay, whereas the conventional heating takes place for more than 3-4 hours. And this is taken from the literature. The black curve is for the microwave sintering, and the red one is for the conventional sintering. The third application that I would like to talk about, again, which may not be of relevant to most of you, but this is of importance to India as a country, or the how to deal with municipal waste as well as the hospital waste, consisting of bandages, syringes, bottles, so on and so forth. Okay, this is a subject which requires tremendous amount of what you call importance in the Indian context, because we do generate huge amounts of municipal waste consisting of plastics, papers, bottles, metallic caps, food grains, and so on and so forth. And usually it is collected by the municipalities and they are dumped in the outside of a town or a city. Okay, and it is allowed to rot. Okay, and the people around that area, they suffer innumerable diseases, including skin effects and breathing problems, so on and so forth. And when the material rots, it also leaches into the ground and mixes with the groundwater and contaminates. In the case of hospital waste, generally what is done is that the hospitals, especially big hospitals, they do collect all their waste, and then they give it to a middleman who takes it to outside the city, and the whole thing is burnt off. Okay, and typically the temperatures for burning is 800 to 900 degrees centigrade, and the fumes that are generated can also cause breathing problems for people around that area. But this method of burning is considered as very cheap, and therefore everybody uses this particular technique. What is done in foreign countries is the following. Okay, they take the municipal waste, I mean they take the hospital waste, for example, they crush it into some kind of a powder, mix it with water, and then heat it to a temperature of about 200-300 degrees centigrade. Okay, because the microwave interacts with the water that is present, that is added deliberately, it forms superheated steam, and this superheated steam completely destroys all the viruses, bacteria and microorganisms that are present. And once it is done, then this treated hospital waste are taken away and put in some kind of under the ground. Okay, and that way the leaching and other things are not there. And but I have not come across anybody who using this type of technology being practiced in the country. And it adds to the cost definitely, but at the same time it also ensures that the waste do not affect the community or the society at large nearby. So the question that we have now is what exactly are the challenges that we have for adopting microwave-based techniques in the Indian context? One is definitely the initial capital investment. Most of the people do believe that the initial cost of capital investment is very high for microwave, and therefore that is one of the challenges. One way to go about it is that it should be subsidized by the government, especially for hospitals and other users, so that we have a safer way of disposal of the waste. Okay. The other challenge that I see is that for very large samples, microwave heating can be a problem, because a lot of products do have very large sizes in dimensions, and getting uniform heating for the large sample is still a challenge. And that is one way of there is a need to improve the system development using microwaves for such type of large samples. And third, and the most important thing, is that there is a lack of awareness of the benefits of microwave technologies to the people. This is because it is a very specialized area, and a platform like this helps us in propagating the good knowledge about this subject, and at the same time spread the awareness to the society for what exactly are the challenges that are affecting our society, and how to overcome using modern techniques such as microwave heating. Thank you.
Thank you, sir.
Yeah.
So the platform is open for discussions. If you have any queries, the participants, you may ask now. As even the mute restrictions are also open, I request the participants to kindly ask the questions. The mute restrictions have been.
Yeah.
Good evening, sir.
Yeah.
First of all, thank you so much for giving the information related to micro joining techniques.
Yeah.
and you have talked about the microwave sintering.
Yeah.
I would like to know if there are any chances to use the microwaves to join the materials, and if yes, what will be the future and how we are looking for it.
I did not understand. What is the, can you repeat the question?
Uh, we discussed how we can use the microwave joining
Yeah,
or
microwave
microwaves
joining.
for
Yes,
sintering.
yes, yes.
Yes.
Okay, yeah.
And what is the current scenario and how we can implement in the future? Because in case of my joining, we
Okay.
need to customize as per the job
Yeah.
outline.
Okay.
But it is not feasible to go for the micro joining because we are using in a customized environment,
Okay.
the oven we can say.
Now,
But it's not.
let us understand the principle that is involved. Okay. Let us say
Yes.
that you want to join two pieces of metal. Let's say aluminum oxide. Let us say or aluminum metal. Okay.
Yes, sir.
It could be any other metal also, but let's, as an example, let us take that we want to join two pieces of aluminum metal. Okay.
Okay.
So one way is that you create an interface in the middle. Okay. Okay. And
Okay, sir.
let us say that I take the same aluminum. Okay.
Okay.
Incorporate, let us say, a material like silicon carbide in that.
Okay.
Okay. Apply a paste, I mean, make a powder of it, mixture of it, and apply a paste type of thing between
Okay.
the two pieces that you want to join.
Okay.
Then that particular region you heat it to a high temperature using microwave.
Okay. Okay.
The silicon carbide in the aluminum metal which you have added, okay,
Okay.
will absorb the microwave radiation
Okay.
selectively,
Yeah.
and then it will slightly melt the aluminum metal.
Okay. Okay.
And once it melts, and then when you remove the microwave, it cools down.
Okay. Yeah.
So the aluminum and aluminum will join.
Okay. Okay, sir.
So what I am trying to say is the following: that one has to be a little bit innovative
Okay.
in making such process steps to
Okay.
our advantage.
Okay. Okay.
So similar type of thing can be done between two dissimilar metals also if required.
Okay.
Can be done used for composites also. Yesterday, I mean the other day there were questions about
Yeah. Yeah.
whether the microwave can be used for composites.
Okay.
So suppose if you are using a carbon fibers are microwave absorbing material, so you can use it, okay, to process materials.
Okay. Okay.
Okay.
Okay. Thank you, sir.
Yeah.
Yeah. Any more questions? So in chat box, one question has come, sir.
Yeah.
Point
Point to point application of microwave, is it possible? What does it mean by point to point?
Malagada Patil, can you just elaborate on that? You can answer.
Sir,
Yeah.
in welding and all, we apply point to point for joining and all.
Yeah.
Same thing can be applied in microwave application to join the
Yeah.
metal
Yeah. 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 Yes.
for a particular point, sir.
Yes. Yes.
Okay, sir. Thank you, sir.
Yeah. I want to wholeheartedly actually thank sir because just morning I connected him and so I think he has spent some time in preparing and all that stuff. So he has sacrificed a lot today's Saturday weekend.
I am the 12th man actually. I am not in the team.
But I want to place it on record that you are the star batsman for this FDP. Because from Thursday I received personal messages complimenting about the sessions on
No,
Monday.
thank you very much. I mean, it's all your kindness.
We were looking to bring you again,
Yeah.
and they say, no,
Yeah,
cosmos,
sure.
and it has made you to bring again on this during this FDP itself.
Yeah. Yeah.
So
Actually, probably Prakash would have given a better talk on this than me. But with whatever the constraint that I had within a short time, I was able to take his slides, modify a little bit here and there, and made it. So if there are any shortcomings, it is my fault, and I apologize for the same. But I thought that the general awareness of microwave should be useful to everybody, and as a society, we need to make improvements on all sectors, not just in metallurgy or ceramics. The health of the public is also very important, and therefore awareness on these type of aspects is extremely important.
yeah, so we would like to bring you in future also, and
Yeah. Okay. Okay.
like
Thank you. Thank you.
more and more audience from different sections
Yeah.
to interact, engage with you, so that they get awareness on
Yeah.
what's happening, what is expected.
Yeah.
So
I,
sustainable.
I just for, since you have made that point, I would like to say that I'm also familiar with uh, lighting related subjects like light emitting diodes. I'm familiar with other aspects of what you call materials, including ceramics and other things, not only with microwave, but the physical principles, the applications, and so on. And also on Six Sigma, as well as on, let us say, how to write research proposals. I think I gave a talk about a couple of years ago on that in this type of forum for the faculty members. And many of you would be interested in getting grants from the government, and there is a particular way of writing the project proposals so that your chances of getting the approval for the grants will be higher.
On this particular topic, we would definitely like to have you here at the institute
Yeah.
in near future.
Yeah. Okay.
A lot of young people, young
Yes. Yes. And also, I mean, I think the colleges and the universities in Karnataka are very weak in this aspect. They have all the knowledge and expertise, but they don't write impressive project proposals. And in the process, you lose getting government aid. So a little bit of information and knowledge in that particular field will definitely help you in the future also for writing good project proposals.
Definitely, we'll be having you here, sir, on
Okay.
next, on this particular topic, to talk on
Okay.
this particular topic. And one more thing, sir.
Yeah.
You are required for our validity function later at around. I'll get
6:30, right?
6:30. 6:30. Yeah, 6:30.
Okay, I'll join again at 6:30.
Yeah, yeah, yeah.
But
Because
if you
we'll
want,
be
I can continue for a few more minutes on something else, general talk.
anyone wants to know anything from sir, because this is the opportunity where you can talk to sir. Actually, he's not reachable. It's very difficult to reach to him. So because of our contacts with industry and all, we could speak to him so easily. Otherwise, it's very difficult to get access to sir. So this is the time now. If anyone wants to ask anything, please ask. We are having another 2-3 minutes. You can ask, please. I think restrictions have been removed. No, restrictions are removed. Anyways,
Yeah.
in validity sanction, sir will be again joining us. So during that time, you can jot down few points and you can ask during that.
Okay. Okay. Yeah. Thank you very much. Thanks to everyone. Okay.
Thanks a lot, sir. Thanks a lot.
Bye bye.
Bye, sir.
Thank you very much, sir.
Yeah.
Now, I will take 1 minute break and I will request our next speaker, Professor Anbukkarasi Madam from IIT Dharwad. She'll be talking specifically on SEM characterization and XRD analysis. So, on our request, she has joined because there was some popular demand from few of the audience participants that they would like to know more in detail on SEM characterization and XRD. So after that session, we'll be
कुंदा काय करवतीरा
Vasant Kumar sir, Dr. Vasant Kumar sir.
I am muted. Yeah, I am muted. So the restrictions are on again. Now what we can do is we can move on to the next session, and after that we will be starting with validatory session. After the validatory session, we will be having the online test. Okay. And we will be instructing you before the start of the test how to go about how to log into your portal, ATAL FDP portal, and there where you will be getting these options to answer the test. We have uploaded the question paper there, so you'll be getting the access to that. Where you have to answer it. Okay, that is at around 7 or something like that. After the validity session. Immediately. Yes. हाँ. इसी में ही जाना आया. Right, she's the face. Yeah, I welcome now Anbukkarasi madam from IIT Dharwad. Before we start with the session, and again, we have made a special request to her, and even after her busy schedule, she has taken up this during this weekend. So I thank her for that. Before we move on, I request our co-coordinator, Professor Ganesh, to introduce Anbu madam.
Yeah, good evening, one and all. So now the next session will be, the resource person is Anbukkarasi Rajendran ma'am. She's an assistant professor in mechanical engineering department at IIT Dharwad. So she'll be delivering the lecture on the specifics on characterization by electron microscopy and XRD analysis. Over to you, ma'am.
Shall we begin?
Yes, ma'am.
Yeah. Thanks for the introduction, Dr. Ravindra.
Yeah, madam, you can share your screen.
Can you able to see my screen?
Yes. Yes, we can see this.
Can you able to see? My voice is audible? Hello?
Yeah, audible, madam. Yes.
Audible, right? Yes. Shall we begin?
Yes.
Thanks to everyone that again we are joining for discussion on the same topic, but little specific into detail about the characterization. Whatever we covered last session, same thing with the little more detailed analysis and special requirement for any special sample preparation, etc. Everything I like to point out in this session. So yeah, this one already I have shared you that we can classify the complete characterization under two categories. One is destructive, another one is non-destructive. So all our microstructural analysis and mechanical testings are coming under destructive analysis category because we are cutting the samples and do the analysis. And in case of non-destructive, we need not to cut the sample as it is in the component form. We can go for the characterization to study the internal structure. Okay, so yeah, as I mentioned, whatever we discussed, including that, some special techniques and analysis I like to cover. Okay, so before I get into that, I like to give you the overview or flowchart of the materials or product development. We know the procedure how from extraction process to the final product, right? So the extraction of any metal or material get into the final product, intermediate process is casting. Then from that, it can be taken to the manufacturing process. Let me open my pointer. Yes. Yeah. So the metal can be extracted or you can derive from the nature how it is available, and intermediate process you can do get into the concentrated of that particular element. So in specific metallic materials, so direct final products can be formed by using the same process itself, or else we can go for some manufacturing processes, rolling, forging, everything. Then forming operations are required to get into the final product. In other side, you can get the metallic materials in the form of powder, and you can shape into to get the final product. Why I brought this flowchart here, the characterization is not sticking to the final product alone. So at any stage, not only the metallic material, this typical chart is representing the product making by a metallic material. So somewhere here, even polymer reinforced composite, ceramic reinforced composites also can be made. So any material, when it goes for the final product, intermediate multiple processes it will be taken through. So your characterization can be at any point. So it can be in the extraction process itself, or after casting, immediate casting, intermediate process, whatever we are doing, or it can be for the final product also. So based on where we are taking up the characterization, so that decides what kind of sample preparation is required and what results we are looking for that. That will be decided by the stages where we are going to pick the sample. Okay, so already we discussed about the sample preparation, and the basic sample preparation begin with the cutting process and followed by the polishing process. The polishing can be done in two ways. First, in a coarser grid size paper, then fine cloths can be used for the final finishing. Okay. So these procedure regularly we will use for the regular analysis, whatever optical or electron microscope analysis we will take for. In addition to that, there is additional method that electropolishing. Okay, so the electropolishing is even further finer down or finish down the surface to the mirror image. Okay, so this is especially required in case if I am going for EBSC analysis, this electropolishing is required. Same way, there are two methods. Regular etching, already I mentioned in the last class, we will use the regular some chemical, combination of some chemical named as etchant. So the etchant to be used to reveal the grain boundaries, details, everything. So in addition to that, another procedure is there, that is electrolytic etching. Okay, so electrolytic etching, typical galvanic cell coupling you can make in your lab itself. You can take a 2 beakers, fill with electrolyte, or single beaker itself fill with the electrolyte. You can select your anode and cathode. So your sample can be anode, because anode will undergo for reduction reaction. Then you can select a suitable material as a cathode. So you can connect both electrolytically. Then if you supply some voltage, automatically the reduction and the oxidation processes in the respective samples, in anodic and cathodic samples, the reactions will be taken place. If your sample is connected to the anodic source, automatically due to the reduction reaction, your sample, fine layer of sample will be removed from the bulk material. So that's how the electro polishing is happening. The same way you can use some specific electrolyte you can use for the etching process. So this etching process, for regular etching process, you have to go for regular polishing. Directly you can take it for regular etching. Electrolytic etching also require the regular polishing process. Then you must take it for the electrolytic etching. It does not require the regular etching before taking for the electrolytic etching. Same way, electrolytic polishing is required the regular polishing. After your regular polishing, till the cloth polishing, then only you can take for electrolytic polishing. Because this electrolytic polishing only can remove a fine layer. So whatever the bulk burrs or anything damage is there during cutting process, that cannot be removed by electrolytic polishing. So before taking the electrolytic polishing, the sample supposed to be finished with the mirror image by your regular way of preparation itself. So additional point to remember here is, as I mentioned, if it is a small sample or the sample is difficult to hold, you will go for the mounting. The mounting material can be polymer. So the polymer, if it contact with the electrolyte chemical, again that may react, soften, and that it will come and stick to the surface, and that will be non-conductive. Then again that will affect your electrolytic polishing or etching process. So better when you are going for either electrolytic polishing or electrolytic etching, the sample supposed to be free from mounting, that any mold, that you ensure. In case if it is mounted already, you cannot break for some particular reason, you can cover it, mask the mount. So then cleverly, some wise you can select your procedure. You can go for the electrolytic polishing or etching processes. So this is one of the sample. Last session also I showed. This is a part of stainless steel sample from stainless steel to nickel, some dissimilar metal welding site. We could see some grain coarsening in the heat affected zone close to it. Whereas the base material does not affect, little far away. This is the weldment part. So we wanted to see the grain size distribution by using EBSC detector. So EBSC detector will come along with the SEM machine. So this is one of the special detector which is used for calculating grain size distribution, grain size orientation, and many other things that I already mentioned in the last session. So EBSC technique is required the electropolishing specifically. So we must do electropolishing for EBSC analysis. Okay, so if the electropolishing is very fine, good, then you can get a better pattern in EBSC analysis. So EBSC, we used this for measure the grain size distribution in base metal and heat affected zone. It covered the weldment portion also. So yes, so electropolishing is required. So it is a kind of mapping. The mapping is done based on the grain individual orientation. Okay, so the individual orientation and the crystal structure. So the mapping is done. So all the information related to the orientation and size distribution, everything we can get by using the suitable software. So whatever we are plotting by using running the scan by using SEM machine with the support of EBSC detector, again those data should be run through some suitable software to see all the details, and whatever is required from this you can plot. Yeah, as I mentioned, the polishing, the goodness of the polishing, the finishing surface can be identified by the QQC pattern. Once the electropolishing is done, if you load the sample into the machine, you can just hit the point and see the electron beam. If it can produce a proper QQC pattern, then I can ensure that my surface finishing is good. Okay, so the EBSC can give the IPF map. Okay, so then this is grain boundary map and CAM map. Okay, so all the orientation distribution and boundary, grain boundary orientation, like high angle grain boundary, low angle grain boundary, if it is a twin boundary, and grain size distribution, as well as any phases, multi-phases structure are there, phase fraction also I can get from this. Okay, so this is some of the image I have taken from Google. So you can see the grain size variation among the samples. So the grain size distribution, the plot you can get like this. So it indicates that the grain is available from this. This is the minimum you could see in the scanned area, and this is the maximum, and this is the distribution. So this many finer number, this many intermediate number, this many higher number grain size are distributed in the scanned region. Okay, so again, EDS is one of the another detector which is helpful for studying the chemical composition of either matrix or any special feature in the sample. So I can go for either spot or area that already I mentioned in the last session. If it is a spot, I have to go carefully to select my region. So this is one of the precipitate is present in the, this is stainless steel sample. So it is, inconel sample. It is seen with one different phases. So we like to know what would be the composition of this. So we picked the region and we spotted the electron on top of this. So we could able to get the spectrum. So what are the details I can get, or how the machine will produce the data? First, I can load the sample in as polished condition. This kind of analysis does not require any etching process, as well as even electro polishing also does not require. So if I am aiming for some particular element, I can go for, if already I know the element, I can give the input. Otherwise, randomly if I'll hit the machine itself with the database, it will run and it can give the what could be the elements in this. Okay, so we run the spot on top of this, so we could able to see the molybdenum pattern and the chromium pattern. As it is inconel material, some of the nickel is read from the matrix also. Okay, so I can get to know that this particle is enriched with moly and chromium. So I can predict this phase can be enriched with moly and chromium. So the machine, the software can give the detail of each element, atomic percentage and weight percentage both. Okay, so I can get spectrum as well as the quantification of those elements. Instead of a spot, I can go for line. When I'm choosing the line, I have to choose the start point and the end point, and the intermediate, how many points I want. I have to choose. If this is one of the sample corroded when it exposed to the atmosphere. So this is steel, this is iron oxide corroded layer at the top. So we wanted to measure the thickness of the layer. When I'm choosing this layer, drawing a line, I want to know the gradual variation of the composition across this layer. So what I have to do, manually I can give the points, how many points I want to get in the selected line. If I am picking, if I am giving 4 points, the 4 points eventually distributed from the start point to end point. That is the case. I may get one result or data from here, and second may be here, third may be here, and fourth may be here. But in case if it is very finer, I want to see the gradual variation very clearly. So I can go for even more points. Okay, so the points, the overlapping of the points also should be minimal, as well as I should give enough number of points to get a clear variation across the layer. Okay, so again, even line scan also, line scan is a extrapolated version of the point scan. So here only one spectrum we are getting. Same way, for each point you will get one spectrum, and each point composition you will get. In addition to that, we will get the sequence of the composition variation at each point. So I can get an additional information that the variation across the layer within the selected line. I can even plot graph in the form of atomic or weight percentage versus the length I have chosen. Okay. So this already we have I have shown in the even last presentation. So not only the single spot, multi-spot, how I have taken here in a defined line. Here I can go a multiple spot in a random line based on my requirement. Okay, here 2 layers are there and my base metal is there. So I can either I can go line scan to see the variation as given in this case, or else I can go for the spot only. If I am sure that it is continuous and uniform, only I want to check anywhere, any composition. So randomly I can pick one point here, second point here, and third point from base metal. So as I said, for each point I'll get the spectrum as well as the quantification values. So always this EDS composition analysis will give spectrum as well as the quantification data. If I'm giving a line, in additional, I can plot a line also like this. So I have given a line from one side to another side. This is a dissimilar metal. So when I'm giving a line, so each point I got some mass and weight percentage of a particular element. Okay. Particularly, as it is a copper and aluminum dissimilar joint, I wanted to know the variation in copper and aluminum. So only I picked the copper variation from one end to another end, as well as aluminum variation from one end to another. So then I have plotted, so I could able to see the variation. The same sample after heat treatment, I could see some changes in at the interfaces, the same interface after heat treatment. So again, I wanted to see how the diffusion variation at the interface. Again, same thing I did. I could compare and read out the compositional variation at a different condition. So this how this line mapping will helpful. So this was taken by the EDS detector. This was done by using the WDS detector. So already we touched somewhere that output scattered electrons will be received in the form of either energy or wavelength. So there are 2 detectors. One is EDS detector. Normally all the machines, all the people can bear the cost of this. but WDS detector is little costlier, but still it can give even a accurate result than the EDS. So WDS also can give the same information as like EDS detector, same spectrum, quantification analysis, and line mapping. But the same thing is done by the wavelength. The detector receive the wavelength of the scattered electron, then it will plot. So this will have a little accuracy than that, but both detectors will serve the same purpose. Okay, so using WDS detector, we can plot a map. Okay, so the plot again, the map again, EBST map, how it is drawn based on the orientation and crystal structure. Here, this mapping will be plotted based on the composition variation. So I can choose one particular element. I can select the area. Within that area, how that element is varying from 0 to the maximum. The concentration variation of a particular element in the selected area based on its composition concentration, I can get the mapping. So this mapping is called EPMA mapping. EPMA is nothing but electron probe microanalysis. Okay, so this is the same copper aluminum dissimilar joint. So I plotted this mapping for a copper variation. So this is copper side. I could see the enrichment. This color code give me the information like the pink color is the maximum high concentrated uh, region, gradually decreasing. Then this the dark color is indication of a depleted zone. So when I am taking this particular region, the copper variation is high this side and here low because this is aluminum side. So when I am plotting aluminum for the same selected area, so aluminum is depleted here or not available, and copper is, sorry, aluminum is high in this region. Okay, so whatever the intermixing happen at the interface, you can see the diffusion layer with the intermediate color 50-50, means some diffusion I could see at the interface. The same region after heat treatment, how much the diffusion, the concentrated. So whatever I could able to see here the variation qualitatively, how the distribution is there at the interface, I can see by doing the mapping. So this is a kind of a qualitative analysis. This will give the quantitative value of the particular composition. So this mapping is qualitative compositional mapping, which shows the quality qualitatively distributed of that particular selected element within the selected region. Same way, this is done by WDS detector. Same way, I can do the mapping by even using the EDS detector. So it is called EDS mapping. EDS mapping, the drawback of EDS mapping is EDS mapping can show whether the material is there or not, but there the concentration different with the multiple concentration variation cannot able to show. So EDS is very cheap and simple. As I told, EDS detector will be available with many of the people. So directly you can go for a simple thing, direct EDS mapping you can go for. Very gradual variation if you are predicting, then you can go for the WDS mapping. Otherwise, EDS mapping would be fine. So this is the corroded layer of steel sample. So the same sample, same region, we have done EDS mapping as well as the same region was done by the WDS mapping. So this is respective for the oxygen concentration. So you can see the brightness shows the presence of oxygen at the top and dark region showing the depletion of oxygen. Same way chromium, this is the whole thickness of this layer. If you see, chromium is depleted only half of this layer and rest is, there is a presence of chromium. Okay, so iron, partially it is like partially dull, here enrichment. So this is a base material see. So I can see the enrichment of iron here, partially diffused here. It is iron oxide, so partially iron you can see here. Again, chromium from the sample little diffused here. Okay, but oxygen is from the environment. uh, It is reacting from the top surface to the interior sample. So you can see the concentration, high concentration at the top. So EDS mapping will give the feeling of yes or no. But here, how much the gradient? Okay, so in EDS, one single color for one single element. But in WDS, for a single element itself, with respect to concentration variation, there will be a multicolor coding which indicates the concentration in the composition variation. Okay. Yes. So this is also the dissimilar material. Again, the particle, one particle distributed into the another one. So I have mixed one extra metal at the intermediate region. So I wanted to see how the distribution of all the elements. So all three elements I given. So each element is one particular element enriched here, another element only partially distributed here. So like that, copper, aluminum, and the third material distribution, I try to analyze by using the same WDS mapping. And yes, SEM micrograph, as it is, we can see for seeing any cracks, presence of cracks, it does not require any additional sample preparation. In as polished condition, you can see. But if I want to locate the crack, I need to do the etching and see. So this particular crack, I could be able to see close to the interface. This is weldment, this is the heat affected zone. So to locate where the crack is present, so we did etching and see, so we could be able to locate. So in that case, as after polishing, etching is required. So both are under SEM micrograph, SEM analysis. And SEM, the basic machine will come with the SE detector and the BSE detector. If you are feeling that there is some concentrated concentration difference in some particular phases, you can go for a BSE detector, which can reveal the additional phases clearly. Okay, so some of the precipitate in stainless steel, these are niobium rich precipitates in stainless steel. So we could able to see clearly when I'm taking the images in the BSE mode. So there are grain boundary precipitates I could see. So that also we could able to see with the BSE detector. So normal, if there is no phase contraction or there is no feature contraction, directly you can go for the secondary electron mode. Okay, so for the crack, presence of crack also can be seen in secondary electron mode. But the features, if you want to see, you can go for the BSE mode. Okay, so some of the, as I mentioned, yeah, and not only after the product making or intermediate product making, if you are going for any reinforcement like a composite making or powder, this is powder metallurgy component, the powder. So before making the powder size or in composite, if you want to reinforce any ceramic particles or polymer in the metal matrix or polymer into the ceramic matrix, irrespective of any conditions, if you want to see the polymer size, any feature details, if you want to see, directly you can load in the machine without any preparation. As it is, you can distribute the sample on the carbon tape, you load, you can see the size and size of the particles before doing any process. Even after doing process also, the agglomeration you can see, even the powder metallurgy component, you can do like a regular sample preparation and sample preparation, then etching to reveal the internal microstructure. Okay, so again, this is as sintered condition, the powder metallurgy component, but partially it's not properly sintered. So the fractured surface could see the fracture of the particles itself. So this is the fracture surface of the powder metallurgy component. If it is sintered well, you can see the proper merging of, or there is a good bonding between the particles or powder, metals in the form of powder. Okay, so those samples fracture behavior is different because of the proper complete metallurgical bonding between the particles. Okay, so another one is, this is again intermediate layer. So to reveal this intermediate layer means intermetallic layer between aluminum and copper at one particular condition. So to reveal that, I choose an BSc detector. So as I mentioned, if there is a contrast difference or any density difference features you are expecting in your structure, you can go for BSc mode and see or try to capture those images. This is one of the wear tested sample pin on disk experiment. After wear experiment, how it is wear out the one morphology of the one surface of the pin was captured by using SEM. Okay, so as I mentioned, this is one of the ceramic particles embedded into the aluminum matrix. So SEM again used for seeing after the process of composite making. So we could we were trying to see the bonding between the particle and the matrix. So you can choose the region where the bond, the particle and the matrix you can capture. Okay, so you can take it to high magnification and see. And this is one of the spot analysis on the ceramic particle. Okay, again same sample, as it is ceramic reinforced metal matrix composite, we cannot carry out the tensile test, so we did a compression test. So the compression test, so here I am covering two things. One testing method, that if it is a composite material, we like to go for the compression test instead of tensile test. Second one is, even tested samples also you can do for the do the analysis for understanding the fracture behavior. Okay, so some of the matrix region, how it fracture, and the particles also during test it got fractured. So another test is 3-point bend fatigue test. So we wanted to see the background was like the material when we tested under tensile load. So the fracture behavior was quite different. So at the interface, here you can see aluminum copper interface, the failure happened. Then later we could see the propagation along the copper side. We expected it's supposed to propagate through along the interface, but instead the propagation direction got into the copper side. So we tried to understand, we did many other study analysis also to understand the propagation behavior. Okay, so that I'm not going to cover here. So the message is, yes, fatigue test you can carry out to understand such a behavior. So we could plot SN curve. So multiple samples you have to prepare. Each at each stress you have to run the sample. The number of cycle required for fail I can point out. So n number of tests, some at least minimum some 12 or more than 12 stress level you can select, and each sample should be run for a multiple cycles until fracture. Then we plotted a SN curve. So after fracture, each sample, as I said, the crack propagation analysis we wanted to do. So this region, it went to brittle fracture. Okay, so this region undergone for the ductile fracture. So the same sample only, whatever the EPMA mapping, if you can able to recall, so there was a fine intermetallic layer at the interface. As it fell along that intermetallic, it undergone for the brittle fracture. When the propagation through copper, completely it is ductile fracture. Okay, so the ductile fracture we could parted in the region where the propagation can happen along the copper. Okay, so again the same sample, yes. So from here only we could able to come up with that fatigue test. So during tensile test we could see the top layer fractured along the copper, bottom layer fractured along the interface. So how I can ensure that it failed along the interface, how it failed along the copper. So this is the fractured region. Okay, as it is, we taken to the SEM. Okay, this is the cross section of this fractured phase. So wherever it failed with the brittle nature, so we can see the flat mode of fracture. So the ductile fracture is having the dimple appearance. So the flat region, when we did the EDS analysis, by selecting the area, here we didn't do the spot. We selected a big area and we could see the copper aluminum, both the peaks, the spectrum of copper and aluminum we could see from this fractured surface. So it indicates that the failure must have been along this intermetallic layer. Same way, when we did the area analysis, EDS analysis, the spectrum we could get only from the copper metal, means the region is entirely by covered by the copper. Okay, so the failure here two message. One is copper undergone ductile failure, or the ductile failure is happening along the copper region. So that was confirmed by the EDS analysis. So another message is for these things you need not to do any special sample preparation. Cut the sample as it is, you load in a vertical position. Okay, so you can even as it is do the SEM analysis in secondary electron mode. Even DSE mode you can choose in case if it is some composite, other things, some particles or intermetallics you are expecting at this interface, you can go for DSE. Even this is intermetallic phases, I didn't go for backscatter electron mode, because in the same region, if I am covering both two different features, then I can go for the BSE mode to make the contrast. If I am focusing either the intermetallic or the base metal side, then I can choose only secondary electron mode. Okay, so the mode selection and understanding, and as it is you can do how to go for the sample preparation and how to take for the analysis, as well as it is you can do the EDS analysis for certain information. Okay, so the same tensile test can be carried out by preparing the micro tensile samples. If your samples are very smaller, it's not good enough to prepare the macro tensile samples, how we are preparing for the regular tensile test, which will have the 100 mm length. So if I cannot prepare such a big sample, standard sample for my analysis, I can go for a 1 mm thick, 20 mm length. I can go for a micro size of tensile sample. Again, same test can be carried out by the regular UTM machine itself, but I require a special grip which can hold such a small thin sample. If I have a special grip made for holding the sample, I can even perform the same test for a micro tensile sample by using UTM machine itself. Again, as I mentioned, even micro tensile samples can be taken for the analysis like this. Again, this is one of the tensile tested sample. Vertically, we have polished. The fracture happens, so we want to know the fracture propagation in a similar material. This is one of the aluminum material with under different processes. So each processes how the process. In last session, I mentioned some of the aluminum by adding the elements, the nature of the morphology of the intermetallics will vary. So this is one of the example. We made one aluminum casting in one particular process. then it is added up with another elements and different processes. So in each processes, if you'll see at a higher magnification, you can see the differences in the features. So each feature, how it is affecting the crack propagation. So we wanted to understand, because one of the samples showed only 4% elongation, another sample showed 28% elongation. Such a huge variation in the elongation we could see. So which showed the very less percentage of elongation. It's supposed to have failure much earlier, must be under a brittle nature. So how, which one is acting as the weakest point to propagate to make a sample failure as earlier? So we wanted to understand. So we could see the fracture, could see this is the interdendritic region where this needle shape intermetallics are the eutectic phase, it is called the eutectic phase, where we can see with the needle appearance. So that was the crack origin point, and propagation also happened along that. To ensure that horizontal samples we cut and polish, a regular microstructural analysis, same way, polished, as it is a cast sample, it didn't require the etching process, because these eutectic phases can be revealed even as polished condition itself. So we try to do that analysis by doing this way. Okay, so this is one of the TM sample after tensile tested we have taken. So we can see the dislocation pinning over the precipitate particles, how the dislocation pinning happen, and this is some of the region you can see the dislocation now. Here you can see R1 looping as well as the there is a cut through. Okay, so these are the dislocations. Even TM can provide the EDS, TM can provide the analysis, chemical analysis thing. So for particle composition, this is the precipitate. So very finer precipitates, you can see the scale is in nanometer. So these fine precipitates composition even we could able to measure by using the EDS director. But it is attached with the TM, not with SEM. So how the composition mapping can be done for with the variation in the composition, even hardness plots also can be done from one region to another region. So that can give the feeling of the hardness variation, how it is there from one region to another region. Okay, so exactly. For hardness, yes, still the paper polishing is required. It does not require any electro polishing. It does not require any etching process. Same way for XRD analysis, it does not require any etching process or any other thing. XRD requires only like paper polishing till that point. Bulk sample you can take. Before getting to XRD, TM sample preparation I missed to tell. So TM sample preparation, I think most of you are aware of it. We must prepare very thin transparent sample we have to prepare either by hand polishing, then you can go for ion milling, or else focused ion beam FIB technique is available, where TM lamella directly you can mill out from the bulk. Directly you can get the sample which is readily directly loaded into the TM machine for the analysis. Okay, but the drawback of FIB sample is it will be very smaller. Your area will be very area or sample size will be very smaller, so it will be restricted with the area for the analysis. Second thing is ion milling may deposit the sample back over the processed sample. Again, you will end up with some mistakes or error in the analysis. But regular sample, you will get the more area thinned down by hand, then do the tips for making a hole. So that will give a little more accurate, more area, but it is very painful procedure for preparing the TM sample. Yeah, come back to XRD analysis. As I mentioned, it does not require any extra sample preparation rather than the paper polishing. So a bulk sample can be loaded in the machine. Uh, the machine will give the theta value, 2 theta value. Okay, so the 2 theta value will get, for each theta value, what is the intensity peak, we will get the data in the form of ASCII file. So the ASCII file will be loaded in the particular software. The software will have the database of each the element or compound with respect to each theta value. So you have to run the ASCII file using that particular software. Okay, so you can compare the data as it is available in the database and your spectrum, then you can match, you can identify. So this can be compared with your EDS, WDS composition analysis, where you will get only the elements as it is. Each spectrum will be getting for each element in case of EDS or WDS analysis. Okay, if even aluminum copper precipitates are there, you will get one peak for aluminum, you will get one peak for copper. But in case of XRD, copper, aluminum, intermetallics will have, aluminum will have one peak, copper will have one peak, aluminum copper will have an additional peak. Okay, so there the confirmation of presence of intermetallics is much accurate in XRD. So XRD analysis can be again used for measuring the grain size, crystal size. So each spectrum, this is full width at a half maximum. So that value and theta value you supposed to substitute in the formula and you can calculate the crystal size. So again, it is used for the stress measurement. Okay, so the stress, first you have to get the spectrum for the unstrained condition, or the sample is free from stress. The same sample under stress condition, again you have to take. There is a suitable formula, so you have to substitute and by value the strain you can calculate by using the suitable formula. Okay, so I'll stop here. We can move for the question answer.
Yeah, the forum is open for questions now. If anybody is having questions, please ask. You can type in the chat box. Restrict, yeah, kindly post questions. Okay. So the microphones have been activated. So the restriction has been removed. Sandeep Kadane, if any question is there, you can ask. Any questions, please? Padma Kumar has the question. Padma Kumar, you can ask. Just check whether the microphone is unmuted.
Can you speak little loud?
Padma Kumar, can you, or else you type your message, just check.
Sir, now it is turned on. It is turned on. He can speak.
Yeah.
Padma Kumar, you can speak. Padma Kumar, am I audible, Padma Kumar? Can you just type it in a chat box?
You can type it in the chat box, Padma.
Good evening, madam.
Yeah, good evening, sir, please.
It was a nice session, madam. I have a question
Thank you.
regarding the XRD analysis, madam.
Yeah, please ask.
Madam, whatever we fetch the data in expert high score, there is an
Correct.
standard database.
Correct, correct.
Madam, should we update that standard database each and like for is there like that standard
I got
database
your
get-
point. Yeah, I got your point. So for the common available elements, common available precipitates in the known system, already the database is updated with. When you are going for analyzing the new metal or new thing, yeah, again you have to find out, you have to update your database.
Okay, okay, madam. Thank you.
Thank
Yeah, any other questions? Yeah, if so is, we can wind up this session. Again, a special thank to Anbukkarasi madam for taking time out and giving a talk on request on Saturday evening. It's a holiday, it's a break for them, even after the busy schedule she has come. So thanks a lot from the coordination team here, madam.
Thank you
Uh,
so much, Professor Vinay.
Yeah, and we will be having you in future also for a few more events or another session. So
Yeah, sure. You are always. I'm
thanks.
happy.
Yeah,
I'm always happy to give any sessions or be part of your institute for any other activities. Right.
Yeah, our
Thank you
pleasure.
so much to the thanks to the coordinator also, all the coordinators of this program. Really, it is going well, and I could see the number of participants for even in the evening. So many active participants I could see. That motivated me to give accept for this request, and again I came back and
Thank you. Thanks.
really good. Yeah, doing good. Mm. Thank you. Shall I leave the call?
Yeah.
Yeah. Thank you, everyone.
So the overall feedback link has been posted in the chat box. Please fill it, and in another 2-3 minutes, we'll start with the validatory. Another 3 minutes or 5 minutes, we'll start with the validatory. 5 minutes. So please fill the overall feedback which is posted in the chat box. Okay. Now we'll start with the validatory.
Yeah, we'll take a 5 minutes break.
Yeah, we'll take a 5 minutes break and we are starting with the validatory. And after that, examination. So some instructions are there regarding examination. After the validatory, we'll be explaining. During the validatory, we'll explain it. Okay. Okay. Yes.